Welcome. In this lecture, we're going to be making an exercise on pressure drop calculations in a wellbore that has multi-phase flow, and we're considering the case where it has oil and gas and no water. So this is the Excel sheet we're going to use, the template, and the link to this Excel sheet will be provided in the description of the video. So we are going to work on this sheet called Data DF Volga. We're going to be making our calculations using different models. So DF stands for drift flux, and Volga is the slip correlation we mentioned earlier. That is by Semayat and Gashar, and then the slip correlation by Nagu, and lately we're going to use a mechanistic model. So here you see is a well that is producing with this GOR. This is the internal diameter of the pipe. Cross-section area is calculated from the ID, the roughness of the pipe, inclination, we're assuming all the wellbore has the same inclination, is vertical, just to make our life simple. Rate of oil is 1,000 standard cubic meter per day, and that's the rate of gas calculated with the GOR. Then furthermore, we have divided our wellbore in segments. We are using segments of 500 meters, might be too coarse, but we want to make it short in this exercise, but later you can change and discretize a bit more this wellbore. And the temperature we're going to assume is given, and the temperature at the bottom hole is 100 and temperature at the surface is 50. Maybe this was measured, and then what we are doing is we're doing an interpolation between these two numbers to find everything in between. In reality, maybe you should solve this together with the pressure, but we are not doing this in this exercise. Okay, then you have here the pressure, and we have the pressure at the top. We want to calculate the pressure at the bottom. We have cases that we have the opposite. We have the pressure at the bottom. We want to calculate pressure at the top. And here you have all the properties that you need to compute first, the local rates, then you need to calculate the superficial velocities, and then with this you can calculate the lambda, the non-slip gas volume fraction, and the slip gas volume fraction, this void fraction, and then finally you can calculate dP dx. And in this case, we will be using the expression for void fraction by these two researchers. Okay, so the first thing is that let's start. We have here a condition of pressure and temperature, so we can calculate all of our black oil properties and all of our fluid properties, and we go here to black oil tables, and these are the tables we have. And first, what I will recommend always is try to check if they make sense. Okay, so let's first take all of these and we want to make a plot. Okay, and let's put it all the way to the top. Okay, and then we're going to just remove. We don't need so many. We could inspect all of them at the same time. Okay, we're going to leave just one series. In this case is small rs and p. And now we're going to apply a filter, and we're going to say we want to see the data only for a given temperature. Here we have a lot of temperatures, so let's see for this temperature 150. How does it look like? Okay, and you see that actually it goes up and then it stops. Then you have zero, stops existing. So that means that we are in a condition that at that temperature we are working with an oil, right? That we discussed earlier. That if you then increase the pressure at some point, there will be no gas, it will disappear. So at least it makes sense and it has a similar shape. Okay, it doesn't have this curvature here, but it has that shape. Then we maybe see the RS. If it's an oil, then the RS should flatten out. Okay, so then you have that shape, which is consistent with what we expect of the RS. And then we can, for example, look at the BO. Okay, the BO should go up and then should go down because here it becomes liquid. And you see that the saturation pressure, the bubble point pressure, is probably around 200. Okay, for that temperature, for 148. Okay, and that is also consistent with what we should get going up and then going down. Then let's look at the others. BG should simply go down and then it stops existing. Okay, that's also consistent with what we expect. Pg, okay, going down. And then we have the density of the oil, okay, that is changing trend because here it's becoming due to pressure is becoming higher, okay, and due to the liberation of gas is becoming lighter. Density of the gas, it goes up with pressure and then it stops existing. Viscosity of the oil, you have a similar trend. At first it goes down because first it goes up because gas is coming out of solution, but then when you reach the bubble point, then it's affected by pressure. When the pressure is increased, the viscosity is higher. Viscosity of the gas, again going up with pressure, and then it stops existing. And then we have here one property, which is the interfacial tension of oil and gas, which we haven't discussed too much, but this is a property we need for one of the sleep models. It's something that is required. So you can produce this also from the way you produce it, your black oil properties. Okay, this is an interfacial tension, sigma, of oil between oil and gas. Okay, it's another thermodynamic property. So that's how you inspect, and I will recommend you to do that for all your data. So for example, we can go to the 50 now, and then we can see how that looks like. And you see that's interfacial tension, has the same trend. Let's look at the RS, for example. Okay, and you see it has now goes up and flat, but now the saturation pressure at 50, you see it's not anymore 200, but actually it went down and it's yeah, below 150. Okay, maybe 140 something. Okay, so at least that makes sense. And then we can continue with our calculations. So the first step, we're going to calculate our black oil properties here. And for that, we're going to be interpolating on this table. So let's first remove this filter. Okay, maybe remove this chart. Okay, and we're going to make interpolation of this with pressure and temperature. We're going to interpolate and find all the rest of the properties. And what I have put here is where the property is located on that table. Okay, for example, RS is the first property that appears, so it's located in 1, 2, 3. Okay, then for example, viscosity is located 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so you go here and you see, well, RS is in 3, viscosity of oil is located in 9, and so forth. So these are the numbers I'm going to use to say in which column it is. Okay, so this is two-dimension interpol. It's a linear interpolation on that table. And I have to provide first the pressure, then I have to provide the temperature, and this will change when I go down. They should take the corresponding row. Which column? Here it will take this column up here, and I want that when I drag it down, it doesn't go down. Okay, so then I have to lock the row, which will be the number, right? But the column should be unblocked because when I drag it to the right, then I want it to pick this one. The matrix that I need is where the BO tables are, is all of this, and then I block it. The matrix will always be the same. And this is an order that is saying in which order are the pressure and the temperature, if it's ascending or if it's descending. So here you see it's descending, is from bigger to smaller, and also the temperature is also from bigger to smaller. So that order I have coded inside, and it's supposed to be 0 when it's descending. And you see here you find 22. Let's say okay, 22. And let's see if that makes sense. You have a pressure of 28 and a temperature of 50. So also check your interpolation. So temperature is 50, and pressure is 28. Let's look for that case. Maybe it's a bit, pressure is down here, 28, okay, and 50, and you see that is 22. So at least that is making sense. Okay, now I drag it to the right. Drag it to the right. Okay, so I have to block, I forgot to block pressure and temperature. Okay, so here I have to block the column, okay, such that when I drag it to the right, it doesn't hop to the right, but I want it to go down. So I have to block the column, not the row. Okay, then I drag it all the way to the right. Okay, and I successfully found all of my numbers. So let's change a bit here. We're going to make this scientific, and scientific I want also to make the BG and the viscosity and the interfacial tension, and then viscosity of oil. All of these I think can remain the way they are, okay, such that they are easy to read. So we have already all of these properties, and with these properties we can calculate the local rates. Okay, remember, if you remember this expression we were using some lectures ago, we have local rates are a function of the BO properties and are a function of the standard condition rate. Okay, so I have already coded these equations for you, and they are in VBA. You go to these modules and you go to I think it's this PVT. Okay, so then you see that you have essentially these equations. They are programmed here. So Q gas local is equal to BG times the Q standard conditions divided by this factor A, which is this difference, RS minus RV, okay, minus this guy times the oil rate, that is BG divided by that factor, okay, RS divided by that factor. And the same thing for oil. So I have these two functions that essentially are doing this multiplication. So let's call those functions. So say QO local, and here we need the RS, we need a small rs, which is, I put it here RV to avoid confusion, BO, and the standard condition gas rate. This is going to be common for all of them because all of them have the same standard condition gas rate and the same standard condition oil rate. And that gives you that rate in local cubic meter per day. And now for the gas, I do the same. RS, I don't block it, RS, BG, QO standard conditions, and then Q gas standard condition. Okay, these two must be blocked. Let's see if it makes sense. Okay, something changed. I don't know what happened. $22. Well, I think first is okay. First is Q gas, so this should be C9, and this should be C8. Okay, now it's hopefully working. Okay, so now I need to calculate the superficial velocity of oil, superficial velocity of water, gas. So then I divide this one by the cross-section area, which is here. And then I have to change the units because these are in days and these are in seconds. So then I should multiply times 36 times 24 because I'm changing from days. And then I end up with this number, and I just drag it to the right to find out the gas. Okay, so you see the difference is not that much. So essentially here the gas is traveling very slow and the liquid is traveling also kind of slow. Okay, so remember the lambda, the non-slip volume fraction. We covered this in lecture 28. We say that is simply lambda is simply Q gas divided by Q gas plus Q liquid. So we say Q gas, we can use this one, or we can also use the superficial velocities Q oil plus Q gas. And we see actually that we have quite a high percentage of gas occupying the cross section if they are traveling with no slip. Okay, so we will see now, maybe we'll change considering the slip. So if we consider the slip, we're going to be using, as I mentioned, the expression by this expression that was given also in video 28. That is, a void fraction is this ugly function, that is the pressure of the system, the densities, and here you need the sigma, which is the interfacial tension, and that's why we have it in our black oil tables. Okay, this expression by these two researchers. So this is, I already also programmed for you in VBA. So you go here to multiphase, and is this expression, Volga. I call it Volga for the kind of the first three letters of the authors. Okay, and is that. And here I just make one thing is if you put USL equals 0, USG equals 0, I think then you get an issue with this expression. Okay, so then I just say if it's 0, then simply it means that you don't have any gas. Okay, and you should put 0, otherwise evaluate the expression. So then we are going to use Volga. Okay, and then this US liquid, US gas, density of the liquid, density of the gas, to the left, I guess, density of the gas, the interfacial tension, the angle of inclination with the horizontal, pressure, the pressure, it's here, the diameter of the pipe is here, and then we need nothing else. Okay. So you see actually that this tells you that the void fraction is actually smaller than the non-slip volume fraction. And if you remember our notes, we were saying that if we had a few cases here, if this is our case, that lambda is bigger than epsilon, okay, that means that the cross-section area occupied by the gas is smaller, and that means actually that the gas is traveling faster than the mixture, faster than the liquid, which kind of makes sense. Okay. Now to find out the delta P at that location, so then we have to use this epsilon, and we're going to use the drift flux model as presented last lecture, this one by that was in the notes of Harald. And here we say that the delta P delta X is going to be equal to all of these expression. Okay, so here we have the real velocities, we have the densities, and we have this two-phase mixture of density of the mixture, which has a void fraction. And we are going to be neglecting these two, the acceleration term. Okay, so if you go to our Excel sheet again, and we see here the dpdx multiphase flow, I call it, and there you have that equation, okay, where you have two parts, the frictional part, which is this guy, and you have the hydrostatic, which is this guy here, and there you have some checks that are used for, because if you are a single phase gas, then you don't need the liquid, or if you're single phase liquid, you don't need the gas. Okay, but when you have both, actually you have to calculate the velocities of the mixture, of the phases, and then yeah, you calculate the friction factor. And finally here, when you obtain the gradient, then I'm dividing to convert to, because all of this calculation is made in Pascal, so I'm dividing to convert from Pascal to bar. Okay, so let's use that. dp dx is the drift flux model. And then we say, well, roughness, it's this guy here. Viscosity of the liquid, it's someplace here. Viscosity of the gas is here. So here they shouldn't be blocked, sorry, because I wanted to drag it down to apply for all rows. And then density of the oil is here. Density of the gas, USL, USO, USG. The diameter, this one is going to be the same for all, so I should block it. And the angle is 90. And the void fraction that I'm using is this one. Okay, so let's see, roughness, viscosity, liquid, viscosity of the gas, density of the liquid. I think it should be fine. We'll see if we got. Okay, so then that's what I found. These are in bar. You see it's very low per meter, but actually we have 500 meters of a of we have 500 meters between this point and that point. So what we're going to do, we're going to say, well, now we have this one and we have the gradient. We will say the next point pressure in the tubing is going to be this one plus the gradient that you have multiplied by the difference or the length that you have on that segment. So I will say simply this will be multiplied by this one minus this one. Okay, I could have made my life easy and just type there 500, but then when you change here, if you want to change the step, let's say you want to make a longer wellbore, you want to make finer discretization, so then it's easier to change. You see now that the pressure now becomes 40, 500 meters below bar. And then what I can do is I can drag all of this down and then it should work, hopefully. Okay, so you see what happened is that the amount of gas is reduced. Okay, the amount of liquid is more or less the same, but the amount of gas is reduced, which makes sense because it's higher pressure. So then more of the gas is dissolved going back to the oil. The non-slip fraction of gas is also being reduced. And you see that the void fraction is also going down. Okay, and of course, because you have more liquid, then the pressure gradient is increasing. Okay, so now we're going to do, we're going to select all of these. We can make our calculation simultaneously, and we just simply click down, and that's what we calculate. Okay, and you see here, that's the flowing bottom hole pressure, 182. And so here you see at this condition, actually, I have some properties of the gas disappear. So I have 0 for Vg, for density of the gas, viscosity, etc. So that means here I have simply single phase. If you see the rate of gas is 0 and the superficial velocity of gas is 0. So then there is no gas, and because there is no gas, then I have just liquid. Okay, and that's it. We have done our first calculation for flowing bottom hole pressure in multi-phase flow. So now let's see something interesting that I have also here. I have a flow pattern map that is what this is the one presented in class that is only for this one is only for, I think this is water and air. Okay, 90 degrees going up, so it might be not so applicable for this case, but still I think we can get some interesting observation. So for example, you see here I have plotted this series of points that are the superficial velocities of gas and liquid, okay, on the chart, on the flow pattern map. And these are initially at the wellhead, but then when I'm moving down, the superficial velocity of gas is going down. I transition from a slug pattern to a bubble flow regime. Okay, which is quite interesting. The flow pattern map, we are not sure if it's very valid because it's changing, the properties are changing along the tubing, the pressure is changing, the diameter is the same, but at least it gives you, qualitatively, it gives you an indication what's happening in the wellbore, transitioning from slug to bubble. Okay, here you have the pressure. I don't know why it got damaged. Okay, so here you have the pressure with the depth. So you see you have the 28 and then it's going down. And then you see here as I have gas, it's more curved, but then when I start to have a liquid dominated, okay, around 2000. So let's say what happens at 2000. Okay, 2000, I'm getting, see that it's becoming relatively low, okay, down to 20%. So that now is becoming like a straight, okay, with constant slope. And that means that I have like more and more liquid until finally I have just liquid. And then this is the gas volume fraction. If I use the slip or the non-slip, you see initially here there is a big deviation, but then when I go and I have less and less gas, actually the gas travels at the same speed velocity as the liquid. And we could say maybe that here these two are different up here, but then here they become very similar. There is almost no slip according to this correlation. Let's say what else do we have? We have the PT diagram And we have our conditions. Remember, again, this got all screwed up. But here we have our conditions of pressure and temperature. We start with 28 and 50, and then we know we have to end up at 100. Okay, but this is the transition that I have, and I have here two-phase region. This is the bubble point line and the dew point line and the critical point. And then I transition from two-phase to single phase. So now our next step, now that we have this working sheet that we have made our calculations of flowing bottom hole pressure. What we want to make is that if, remember that we need this curve, that is the curve of required pressure at the bottom of the tubing, and this is made for a constant wellhead pressure. Okay, so this is for wellhead pressure equal constant. Okay, so we need this curve for making our flow equilibrium calculations. And we have, so far, we have just one point. We have 1000. So we want to know what happens when I increase or I decrease that rate. So one way to do it, I can simply come here and say, well, this is for 1000. So this will be our, I call it this curve, I call it the VLP, okay, the vertical lift performance. Some people call it the tubing performance relationship. Maybe that's a better name, tubing performance relationship. Okay, and we have, well, let's start first with a very low value. Okay, let's say with something like 100. Okay, then I calculate, I find 218. Okay, so let's copy that. This is going to be a bit tedious. And then I copy this number to 18. And then let's try, for example, with 250. And then I got 200. And so forth. And I will repeat that to all the way to a high value, maybe 10,000, 5,000, and see you in a while. So I have finished now the calculation. I have substituted all the way to 6,000. We could not get to 10,000 because actually the table, the Blackwell table, has pressures all the way to 300. I think that's the maximum. So when you go above 10,000, the bottom hole pressure actually becomes higher than 300, and then we cannot interpolate there. Okay, so the maximum we could go is at 6,000. But if you see here, these are the points for each one of them that I got from this using this correlation, and you see the nice behavior we found, and that will be the TPR for a wellhead pressure of 28 bar. Okay, then we can also change that wellhead pressure to see how it will look like. So let's maybe do that. So we do wellhead pressure, and this will be 28. This is in bar. And let's try something that might be later, lower, 10, or maybe something that is bigger, 50. Okay, so these are the wellhead pressures that we're going to try. And this we can also try, well, 10. I don't think we can try 10 also because the Blackwell table goes down to 28. So let's try just with 50, and maybe let's try with 70. Okay, so let's try that. Let's say, well, now will be 50, and let's try with 70. For that, I just simply come here, and then I let's put here 50. Okay, you see already we have an issue with 6,000, but let's try with 100, was the first one. Okay, 241, and again, bye-bye, and see you in a while. So we're done now with the 50, wellhead pressure of 50, and I was substituting all of these rates here for 50 now. And you see that actually this is a curve for 50 that you see it goes up, but actually has kind of a similar trend going down and going up. So now we will do for 70, and that will be the last one we'll make. See you. And we are finished with wellhead pressure 70. See here, I could not get more than 3000 because if I want to get in 3000 already, this pressure at the bottom hole is greater than 300 and I cannot interpolate on the table. But still, we can get some very nice curves. You see how the curve with wellhead pressure increasing is simply getting shifted up.